Okay, in section 8.3, we're going to move from arithmetic sequences and series to now talking about geometric sequences. So, what's the difference? Well, very quick review of arithmetic sequence. An arithmetic sequence is just a list of numbers like this, and the reason it's an arithmetic sequence is because it's plus 5. There's a common difference, right? Plus 5, plus 5. You're adding the same amount every time. Well, with a geometric sequence, each term is multiplied by a constant number, and this constant number is called the common ratio, to get the next term. So, for example, let's say that we started at 2, and then the next number is 6. If this was an arithmetic sequence, then the common difference was 4, and the next one would be 10, right? 2, 6, 10, 14, go up by 4, up by 4, up by 4. But this is a geometric sequence, and you're multiplying by a constant number. So what did you multiply by to get the 6? You multiplied by 3, so you just keep doing that. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162, etc., etc. Or you could stop right there, but I'll put ... Okay, so in all these cases, you are multiplying by 3, and multiplying by 3, and multiplying by 3. So that's your common ratio. Okay, the formula you're going to use for these is right here. There, that's better. So T sub n equals A times R to the, this is all in exponent position, n minus 1. Okay, so what does all this stuff stand for? Well, we've seen most of it before. You know what A is equal to. It's the first term. R you haven't seen before. It's the common ratio that we talked about up here. N is the number of terms, just like before, and T of n is the nth term, or the general term. We talked about that, and just like we said before, it's often the last term. Okay, not always, but it's often the last term, or at least the last term that you're interested in a sequence. Okay, so we'll use the formula in just a minute here, but first of all, let's explain a few more things about geometric sequences. They can be infinite, so actually the one I drew up or wrote right here is an infinite sequence. I guess I could do a different one. How about 3, 6, 12, 24? What's the common ratio? 2. I'm multiplying by 2, multiplying by 2, multiplying by 2, ... There, it's an infinite geometric sequence. Finite, how about this? 3, 6, 12, 24, stop. Right? How about increasing? Well, look at this. These are all increasing too. I could write these again. Either one of them we want. These are increasing sequences. This is an increasing infinite geometric sequence. This is an increasing finite geometric sequence. Okay, decreasing. So if we started at something like 100, what could we multiply by, right? You have to multiply, not divide. You have to multiply by a constant number. What would be a really easy number to multiply that would make it smaller? How about a half? Any fraction will work that's less than 1. But how about a half? So it would go 100, and then it would go 50. If you multiply that by half, you get 25. Multiply that by half, you get 12.5. Multiply that by half, you get 6.25, etc., etc. You could stop there, or if you want to make it infinite, put ... on it. If you were to graph that, so let's say that this point right here is 0 and your 100 is right up there, right? And so your first term was 100, and your second term is 50, it's half of that, and then your third term is half of that, and the next one's half of that, next one's half of that. You see what's happening? It's getting closer and closer and closer to 0, but it's never actually going to reach it. It's a paradox. There's been stories about that, about cutting something in half and cutting something in half, and it gets closer and closer and closer to 0, but it never actually reaches 0. And what this is called is it's called convergent. If something it converges, it gets really close to, and this is convergent towards 0. In this case, it won't always be towards 0, but it's convergent towards 0 in this particular case because it's getting closer and closer and closer to 0, but it's never quite reaching it. Okay, you could also have a geometric sequence that's not increasing and it's not decreasing. Weird. What would that be like? Well, what if I started at 1 and my next number was negative 2. What's my common ratio? What did I multiply to get negative 2? I multiplied by negative 2. So if I multiply negative 2 by negative 2, I get positive 4. If I multiply positive 4 times negative 2, I get negative 8. Next number would be positive 16, then negative 32. And either dot 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 or we'll just stop there. So let's graph that and see what that looks like. So again, this didn't need to be so big, but that's my 0 right there. So it started out at 1, so it started out about there, and then went to negative 2, so somewhere around here, and then it went to 4, so I mean this isn't totally accurate, and then 8, and then 16. You can see what's happening is it's going like this. Okay, and it's going like that, and that, it's going to just keep doing something like that. So this is not convergent, it's not getting closer together, this is divergent. It's moving further and further apart. Now this is not increasing or decreasing, because if you look at it, at this part here, oh, it's decreasing. Oh no, now it's increasing again. No, it's decreasing. Whoops, you're wrong. It's increasing. See, it's neither. Or we could say it's both, but really we say it's neither. Alright, so those are all the different possibilities, I suppose, that there are with geometric sequences. Let's answer some questions. The first question is, find the common ratio. So, common ratio, remember, is the R, and the way you get the R is, you take any two consecutive numbers in the sequence, and this time you won't subtract them, you will divide them. So if I take the second one, negative 100, and I divide it by 400, you could put that in lowest terms and get negative 1 over 4, or we could make it a decimal, negative 0.25, and you're done. Someone beside you, let's say a student beside you, didn't use those numbers. They used 25 and divided it by negative 100. If you put that in lowest terms, you get negative 1 over 4, which is negative 0.25. And the same thing if you did with the third one. If you did negative 6.25 divided by 25, you would also get negative 0.25. So that is your common ratio. Okay, determine the 12th term of this geometric sequence. Okay, let's start by writing down what we know. So the things we're interested in our formula were A and R and N and T of N. Let's see what we know. So A is the first term. Do we know the first term? Yes, we do. It's 512. R is the common ratio. Do we know that? Well, not just by looking at it, but based on what we just did in the last question, we can figure it out. Take any two terms and divide the second one by the previous one. So how about negative 256 divided by 512? Now, if you're good with fractions, you can probably see right now that it's negative 1 over 2. Or if you couldn't see that, just divide it. Negative 256 by 512, you'll get negative 0.5. That's fine too. N. How many terms are we interested in? I mean, this is an infinite sequence. It goes on forever. But if you look, we're interested in the 12th term. So what N is 12. Now, do we know what the 12th term is? No, we only know the first four. This is what the question is. What is the 12th term? So we don't know Tn, but we could be a little more specific. Instead of calling it Tn, call it T12. This is what we're trying to figure out. What's T12? Okay, so we go back and we look at our formula, which will have disappeared. There it is. And that's what we're going to use. So let's remember that and write it down here. Tn equals A times R to the n minus 1. And let's plug in what we know. First of all, we're not going to call it Tn, we're going to call it T12. We want to know the 12th term. We know the first term, it's 512. Times, we know what R is, it's negative 0.5, maybe I'll put that in brackets. And then in the exponent position we have n minus 1, and n is 12, so 12 minus 1. So that equals 512 times negative 0.5 to the 11, obviously. Now be careful. You don't want to go 512 times this. You have to follow BEDMAS. You have to do the exponent first. So you would get 512 times negative 0.5 to the 11th power. Wow, you're going to need a calculator for that. And when you use a calculator, you're going to get something like negative 0.00049. That's a 4. And once you multiply that, you're going to get what T12 is, and it equals negative 0.25. Okay, next one. If the third term is 54 and the sixth term is negative 1,458, then find A, where A is the first term. So we did something like this before with the arithmetic sequences. We're interested in 6 terms total, so let's write them down here. 6 terms. And what we know is that the third term is 54, and the sixth term is negative 1,458, and we want to know what this term is here. the first term. So just like we did before, you could ask yourself, what do you have to do to this term to get to that term? So in an arithmetic sequence, you'd have to add the common difference. But in a geometric sequence, you would have to multiply by the common ratio. To go from that term to that term, multiply by the common ratio. To go from that term to that term, multiply by the common ratio. So our equation we're left with is 54 times r times r times r. That's a faster way of saying r times r times r. Not 3r, but r cubed equals negative 1,458. Now, again, this is fine to do this method like this, but what if it wasn't term 3 and term 6? What if it was term 3 and term 60? How would you do that? So again, we want to focus on how did we figure out that number there? Well, the way we got that number there is we took the terms and we subtracted them. So if it was term 3 and term 60, the only thing different would be 54 is the starting number, but it would be times r to the 57. 60 minus 3 is 57 equals negative 1,458. Okay? But again, usually they'll be very close together like this. Okay, we have to solve this now to figure out what r is. So let's divide both sides by 54. And if you do that, you're going to get that r cubed equals negative 27. Now, what's the opposite of r cubed, of cubing something? The opposite of cubing something is cube root. So we do that to both sides. So the cube root of r cubed is r, and the cube root of negative 27, what's a number that multiplies by itself 3 times to get negative 27? Well, it must be negative. It's negative 3. So that's what r is. Okay, great. Now that we know what r is, we can fill in some of these blanks. We can fill these in even though we don't need to, but why not? 54 times negative 3 is negative 162. Negative 162 times negative 3 is positive 486. And positive 486 times negative 3 equals negative 1,458. Okay, what if we wanted to go the other way? Instead of multiplying by 3, multiplying by 3, multiplying by negative 3, multiplying by negative 3, we could divide by negative 3, divide by negative 3. So 54 divided by negative 3 is negative 18. And negative 18 divided by negative 3 is positive 6. That's the answer. That's what A is. Again, though, what if it wasn't term 3? What if we didn't want to go divide, divide, divide? Because what if it was term 30? We don't want to divide 30 times. You could use that formula. This formula right here. And you could use one of these values right here. Let's use this one. Okay, why not? We'll use that. So our T3 is 54. So let's write down what we know. T3 equals 54. So obviously n, we just change n to 3. N is 3. A we don't know, that's what we want to find. And R we just figured out is negative 3. If you plug these things into here, it'll work. T3 is 54, so that goes over here. A we don't know. R is negative 3. N minus 1, so it's 3 minus 1. So 54 equals A times... what the heck, I'll do the whole thing. 3 minus 1 is 2, so 54 equals, negative 3 squared is positive 9a, right? A9 or 9a, then divide by 9 and you get 6, which was exactly what we said here. So that works as well if it wasn't term 3 but was term 30 or 28 or something like that. Alright, let's move on. How many terms are there in the following geometric sequence? So again, I like to start by writing down what I know. Do I know what the first term is? Yes, the first term is 4. Do I know what the common ratio is? Well, I can easily figure it out. Just take the second term, divide by the first term, and I've got the common ratio is 4. Do I know how many terms there are? No, that's what the question is. Do I know what Tn is? That's like the last term is often what we're looking at. Yeah, we know the last term. The last term is 4,096. So we'll use our formula and plug in what we know. Tn is 4,096. A equals 4 times R is 4. Whoops, sorry. 4 times 4 to the n minus 1. Okay, to solve this, the first thing you need to do is divide by 4. And if you do that, you'll get 1,024 equals, so that took care of this 4. We're still left with 4 to the n minus 1. Okay, now we get to something weird. What we have is an exponent with a variable in it, an unknown in the exponent. And you can solve this. The way you solve this is by using logarithms. Now, there's just one problem. We don't teach you logarithms until pre-calculus 12. So, they decided to put this topic in grade 11 and they decided to put logarithms in grade 12, and you need logarithms to solve this. So you might say, well, just quickly teach us logarithms and we'll use them. It's really hard to teach you logarithms quickly. They're one of the hardest things in grade 12. So what you're going to do to solve this is not logarithms. Since you don't know logarithms, you're going to use the good old guess and check. So what you're going to do is you're going to ask yourself, 4 to some power equals 1024. 4 to what power? Well, let's just try. 4 times 4 is only 16, times another 4 is 64, times another 4 is 256. I mean, you could use a calculator for this, obviously. And times another 4 is 1024. In other words, 1, 2, 3, 4, 5. 4 to the fifth equals 1024. So 4 to the fifth. So this n minus 1 bit right here, the exponent, right? The exponent is a 5. So n minus 1, which is the exponent, has to equal 5. Hope that makes sense. And now if I add 1 to both sides, it'll actually be n equals 6. That's your answer, is that n equals 6. So we guessed to figure out what we have to raise 4 to get 1024. And we found you need to raise it to 4 to the fifth. So the exponent is 5. But the equation tells us that the exponent, which is equal to 5, is also equal to n minus 1. So we make those equal to each other. 5 equals n minus 1, and then we add 1, we get 6. It's always going to happen. You get the one bigger like that. And yes, you'll have to guess and check unless you want to learn logarithms. I can help you with it if you want, but I'm not going to teach it to everyone. Okay, last question. What value of x in these three terms, we have three terms here, x, 2x plus 2, 3x plus 3, how will it form a geometric sequence? Like what values of x will make it a geometric sequence? Well, to be a geometric sequence, it needs to have the same common ratio. And to get a common ratio, we've said it a couple times, you can take the second term, 2x plus 2, and divide it by the first term. Or you could take the third term, 3x plus 3, and divide it by the second term, 2x plus 2. And if it's a geometric sequence, what should you know about this amount and this amount? They should be equal. Hey, what do you know? We're way back to chapter 1 when we're solving rational equations. How do we do this? Well, we have to look for our non-permissible values. Non-permissible value here is just 0. X cannot equal 0. Non-permissible value here, 2x plus 2 is not allowed to equal 0. So if I solve that, I would subtract 2 from both sides and get that 2x cannot equal negative 2, and then I divide 2 on both sides and get that x cannot equal negative 1. So our non-permissible values are 0 and negative 1. Okay, next step. Find the lowest common denominator. Well, the lowest common denominator is x and 2x plus 2, and what we're going to do is multiply both sides by that. X, 2x plus 2, x, 2x plus 2. Reason we do that is because these will cross out over here, and you're left with 2x plus 2 times 2x plus 2. It's kind of odd, but that happens. And on the other side, 2x plus 2 cancels out with that. You're left with x times 3x plus 3. Okay, over here you got to do mountains and valleys. So you will get 2x times 2x is 4x squared. 2x times 2 is 4x, and 2 times 2x is also 4x. So 4x plus another 4x is 8x, and 2 times 2 is 4. On the other side, you just have to do mountains, and you get x times 3x is 3x squared, and x times 3 is 3x. Okay, it's a quadratic. We want to get everything to one side. So subtract the smaller x squareds. This is an x squared here. Subtract the smaller ones to keep them positive. So subtract 3x squared on both sides and subtract 3x on both sides. And what you'll be left with is x squared plus 5x plus 4, and what's left on this side is nothing. What do you do next? When you're solving quadratics, once you have it equal to 0, you factor. This is a simple trinomial. So, two numbers that multiply to 4 and add to 5. Well, first of all, it'll be x and x. Two numbers that multiply to 4 and add to 5 are 4 and 1. 4 in the first one, 1 in the second one. Bring down the plus. A positive times a positive equals that positive 4. Okay, either, using the zero product property, either x plus 4 equals 0 or x plus 1 equals 0. If it's x plus 4 equals 0, then x has to equal negative 4. If it's x plus 1 equals 0, then x has to equal negative 1. Compare them to the non-permissible values. Hey, x cannot equal negative 1, so you need to get rid of this answer right here. and what you're left with is x equals negative 4. Not sure if it's true? Let's try it out. The first term was x, which would be negative 4. The second term would be 2x, or 2 times negative 4, which is negative 8, plus 2 is negative 6. And the third term would be 3x, 3 times negative 4 is negative 12, plus 3 is negative 9. If you divide negative 6 by negative 4, you'll get 1.5. If you divide negative 9 by negative 6, you also get 1.5. The common ratio is 1.5 in this case. It worked. Okay, that is it. So that is what you need to know about geometric sequences.
Love would never leave us alone. In the darkness, you must come out.